So, hello everyone. I'm Shaghayegh, a second-year PhD student in Rutgers University. I'm here to present one of our works that I did in collaboration with another PhD student, Alireza Nooraypur, under supervision of Professor Bajwa, Professor Mandayam, and Professor Wu. The title of my work is proposing a metamaterial-enabled two-dimensional directional modulation array transmitter for physical layer security in wireless communication links. So this is the outline of my presentation. First, I will briefly talk about the physical layer security.
Let's see, mics are working. They should be working. Can you just? I think this one is.
Okay. The physical layer security, which is the motivation of our work, and then directional modulation and a technique to realize directional modulation, which is through using time-modulated arrays. And then I will talk about our prototype architecture, which is a metamaterial-enabled two-dimensional directional modulation array transmitter. And then as a proof of concept, we just fabricated a prototype and then did measurement on it that verify our idea. So as you know, security is an important issue in the design and use of wireless communication networks. Traditional methods to provide security are based on data encryption methods that incur high complexity and communication overhead. Because a lot of encrypted bits need to be sent and also decoded in the receiver. So, but on the other hand, physical layer security, by taking advantage of using a new transmission architectures, is a good alternative to traditional wireless security methods and can address these concerns. Because it is low cost and also efficient. Directional modulation is a well-known technique to provide physical layer security. Directional modulation, in abbreviation DM, is a transmitter side technology, which means the signal is transmitted in a desired specific angle, while it is distorted in all other unwanted angles. So any eavesdroppers located in other angles will receive a distorted version of the signal and cannot get the information from that. So it can lower the possibility of interception. And the physical layer security can be used in wireless communication systems to provide security. Time-modulated array is one of the ways to provide directional modulation. This type of array is called four-dimensional antenna array because time is used as an additional degree of freedom to manipulate the radiation pattern of a transmitter. And this can be done by putting pin diodes as RF switches in each branch of a phased array, and then periodically connecting and disconnecting the antenna elements from the feeding network. So if you can design these sequences correctly, then you can achieve directional modulation. Previously reported work, time-modulated array-based directional modulation transmitters can only provide one-dimensional physical layer security, and they may limit the applications where two-dimensional secured links are needed. So in this work, we proposed a time-modulated transmitter using a composite right-left-handed leaky wave antennas as antenna elements to achieve two-dimensional scanning. And then by using pin diodes and properly design of switches control voltages, we could achieve directional modulation leads to physical layer security. So composite right-left-handed leaky wave antenna is formed by cascading several CRLH unit cells. The left figure shows the circuit model of a CRLH unit cell, and it can be realized through using an interdigital capacitor and a shunt stop in microstrip implementation, as can be seen here. And this figure shows the dispersion diagram of one CRLH unit cell. As can be seen, the phase constant, which is beta, can be negative or positive depending on the frequency. So, and there is a frequency range that is called the fast wave region or leaky wave region. And in this frequency range, the signal, the injected signal to the unit cell will be leaked to the free space. So it can work as an antenna. So by cascading several CRLH unit cells, we can achieve a leaky wave antenna that shows the frequency scanning capability, because as you can see, the main beam direction is a function of phase constant beta, which is a function of frequency. Then by changing the frequency, we can achieve backward to forward frequency scanning capability. This is the radiation. This is the far-field radiation pattern of our proposed prototype. If we consider the main beam direction is in theta 0 and phi 0, then we can write this expression. SAT is the input signal. We consider it a multi-carrier signal, which is an OFDM signal, a signal that used in wireless communication network. And then the green terms comes from putting the phase shifter along X direction and also switches in each branch. And the blue term is actually the radiation pattern of each CRLH leaky wave antenna as antenna elements. So as can be seen, by changing the phase shifter value and also the input frequency, we can change the main beam direction in two-dimensional space. So we can achieve two-dimensional scanning. So by considering the far-field radiation pattern that we wrote and the objective we want to preserve the signal in a specific direction, which is actually the main beam direction of the transmitter, and distorting it in other angles, we found that if we meet equation 5 and 6 for the unit cell control voltages, which we consider as a UMT is a periodic square waveform, then we can achieve our goal, which is directional modulation. So what is important here is when each switch gets on and off in each period, and also the on-time period of switches should meet these two equations, 5 and 6. And what we expect to see after this is that in the desired angle, only we see that the fundamental frequency will have its highest level, so it will be preserved, and all the other harmonics will be suppressed. While in other unwanted angles, the fundamental frequency level will be decreased and other harmonics level will rise up. And this rise cause distortion of the signal. So if we set the carrier frequency of an OFDM signal to exactly these harmonic frequencies, which means that we are causing some distortion in these multiple frequencies, and then the signal will be distorted in these angles. While in the desired angle, we will preserve the signal because all the harmonics will be suppressed. This is the simulation result that we considered the equation we obtained for the radiation pattern, and also by meeting equation 5 and 6 with and without directional modulation. Without directional modulation, which means we just left the switches on, so we have a conventional phase array system. But with directional modulation means that we meet equation 5 and 6 and put switches in each branch. So as you can see in the desired angle, which is the main beam direction, both of them shows low bit error rate. But in other unwanted angles, you can see that with directional modulation, in comparison without directional modulation, we achieve higher bit error rate. So it means that we are getting better security and we are enhancing the physical layer security. As proof of concept of the proposed architecture, we just build a 1, 2, 4 antenna array. We fabricated 4 CRLH leaky wave antenna by cascading 12 CRLH cells, and with the center frequency of 2.3 gigahertz. This is the measured radiation, normalized radiation pattern of each CRLH leaky wave antenna, as can be seen by increasing the frequency in the fast wave region from 1.8 to 3 gigahertz. By increasing the frequency, we see backward to forward scanning. So it means that as we discussed, the main beam direction is a function of frequency. For the feed network, we have a 1, 2, 4 Wilkinson power divider, and then put the switches in each branch, and then phase shifter, as you can see here, and then finally our CRLH leaky wave antennas as antenna elements. The control voltage for switches, which as I told you should meet equation 5 and 6 and is a periodic waveform, a square waveform, come from actually 2 function generators, and we synchronize them to provide 4 output. And for the measurement setup, we did bit error rate measurement for 2 cases, with and without directional modulation, which means we just left the switches on. So how we did this, we just used GNO radio software interface to implement a specific IEEE standard for OFDM signal generation. And then through a software defined radio, we injected this generated signal to our prototype, which is our metamaterial-enabled directional modulation array. And then the signal goes to the free space. And then by putting another Vivaldi antenna as the receiver, we collected the signal in different angles by scanning the angles. And then through another software-defined radio connected to the receiver, and by using GNO radio software interface again, we finally could get the bit error rate in each angle. This is one of our measurement results. Suppose that the main beam direction is along a Z direction. And then in the shown plane, we just change the location of the receiver antenna from theta negative 90 to positive 90, as you can see here. And then in the desired angle, you can see that both achieve a low bit error rate, while in other unwanted angles, with directional modulation, we achieve a higher bit error rate in comparison with without directional modulation, which means the security will be enhanced in other unwanted angles. And then this is another measurement in another plane in order to show that this is a 2-dimensional directional modulation array. So we just changed the plane and also changed the location of the receiver in this plane, and the result shows here. So in the desired angle, you can see that we achieve a low bit error rate, but still in comparison with without directional modulation, we achieve much higher bit error rate in other unwanted angles. And then again, by setting the phase shifter value to a specific value and also the input frequency to change the main beam direction in theta 0 equal to 45 degree and phi 0 equal to 180. And then did the measurement in the shown plane. As you can see, the same result. With directional modulation, we get better security performance in other unwanted angles. And this is also another measurement we did for another main beam direction. And the result is almost the same. We have better performance by using our prototype in comparison to conventional just phased array. So these 4 figures shows that we can achieve better security performance in 2-dimensional space in comparison with without directional modulation. So in conclusion, I just proposed a time-modulated directional modulation transmitter using CRL-Shaghayegh wave antennas as antenna elements. And then by properly design of switches control voltage, we could achieve two-dimensional directional modulation, can be used in wireless communication links to provide physical layer security. And we fabricated a prototype, and the experimental results show low bit error rate in the desired angle, while much higher bit error rate in other unwanted angles in comparison with without directional modulation, which means that we lower the possibility of interception and so increasing the security in other unwanted angles. Yeah, thank you for your attention to my presentation. Yeah, and if there is any question, I will be happy to answer.
Yes, so have you thought about what if you have multiple receivers that are good? So yes, at the main angle, they're not at the main angle, so they get scrambled data, right? If they put the information together, can they recover the signal?
You mean from the distorted signal?
But you don't have one distorted, you have multiple distorted signals.
So collecting the data from different angles and then getting the information from them. Yeah, because the signal is distorted in other angles, so the constellation map of the signal will be distorted. I'm not sure how they can get the information from this data. Yeah, because this is a traditional method to provide security. You know, if you distort the constellation map of the signal in other angles, then so your OFDM signal will be distorted in multi-carrier frequency, and then the receiver cannot get the eavesdropper cannot get the information. Yeah, but if there is any way to do this, I need to read about it.
Yeah, do you have some thoughts on that? I mean, you're basically saying the receivers can collude and try to figure out what to send. Yeah. That's very interesting. No, I don't think we looked at that. That's very interesting.
Yeah, because it's not like, even though it's random, like the substance that you're picking, but still you get sampled at different spatial.
Yeah, we need to think about it.
A good question. Does the directional modulation have any impact on the power efficiency?
Yes, because in general, when you are using time modulated arrays, which means you are using pin diodes, and pin diodes, they have some off time period and on time period. And this off time, which means that you don't send the signal. And in general, which means that you are lower the power efficiency, but you achieve security. So there is a trade-off between power efficiency and security. Yeah, but with increasing a dimension, which is time, you can achieve a lot of functionalities, but you will lose, some power.
So the on and off time to the switch system are selected in order to cause the thing, right? But they also affect the SNR of the system.
That's good.
Are you aware of any work that tries to jointly optimize the on and off time so that to beamforming and also achieve optimality?
Yeah, because in general, when you are, as I told, when you are using pin diodes, which means that you should have some off time period, right? So in this off time period, in each branch, so you don't send all the signal in comparison with just a conventional phase array that you send the signal in all the time. But maybe there are some techniques by using optimization algorithms to make it better, more efficient. But I don't think that there is a way that we can achieve exactly the same performance in the desired angle, because we are losing some power, in comparison with the conventional one. I mean, by doing time modulation, and you will miss some power in the off time period of pin diodes. But if you can incorporate, you can design your transmitter with other tunable unit cell, maybe using varactors. So maybe you can avoid this. But this is the conventional way.
So one more question. So John, Thank you for the presentation. So your numerical results show that using the directional modulation app to reduce the bit error rate and enhance the security rate. So the question is that can you prove that rigorously?
Prove what?
I missed
Prove what? Sorry, I don't understand you.
yeah, I mean, so you show that your numerical results show that using the directional modulation app reduce bit error rate and have the security. So my question is that can you prove that theoretically?
In the desired angle or in unwanted angles?
Sorry?
In the desired angle or unwanted angles? Because in unwanted angles, it increases the bit error rate. But in desired angles, yeah, I'm saying because when you are using, yeah, you cannot see this. Yeah, I cannot show this, but if you remember in the radiation pattern, we had a UMT that just multiplied. Yeah, here. You had this UMT, right, that multiplied to your radiation pattern in each branch, and then you have phase shifter. So this UMT is a square, is a periodic square wave. So in this direction, when in this time period, when it is off, so it means that you don't send any signal, right? But here you send a signal like a conventional phased array, but in this time period when it is off, which means that it will be 0, right? Then it means that your overall power will be decreased by using these switches in their off time period.